Good morning, everyone. I'm Si Sheng from Shanghai Jiao Tong University. Today I will introduce our work iBlink, smart glasses for facial paralysis patients. We all know that Miss Stallone is a very famous actor in the world, and you may be attracted by his exciting performance in his action movies, such as The First Blood. But do you know Miss Stallone is a facial paralysis patient during his whole life? The complications his mother suffered during his birth damaged his facial nerve and made the lower left side of his face paralyzed, as you can see from this finger. Miss Stallone is not alone. According to the data from National Institute of Neurological Disorders and Stroke, about 40,000 Americans suffer from facial paralysis each year. Facial paralysis can occur regardless of age and gender, and due to the complex functions of the facial nerve system, the symptoms of facial paralysis vary from person to person. However, the exact cause for facial paralysis still is unknown. Most scientists believe that infections cause the disorder. They believe that the facial nerve swells and becomes inflamed in reaction to the infection, which causes the pressure within the Fallopian canal. Since the eyelid on the paralyzed side cannot fully close, the eye will become dry and get infected. This will incur eye damage and even blindness. Most of facial paralysis patients will recover in around 6 months with or without medical treatment, but there are still some patients who will never return to normal. The current treatment for facial paralysis aims to achieve facial symmetry, include job and surgeries, but they are all side effects and controversial. A very interesting observation is that an appropriate electrical stimulation can make people blink. Electrical stimulation itself, because it does not damage the facial skin. To verify this effect, we conducted an experiment on 5 volunteer patients in a hospital using EMG workstation. The EMG workstation can generate a stimulation current impulses and apply them to the facial skin. This table shows a different critical point for the stimulation reaction of different patients. Based on such observations and inspired by the popularity of wearable devices such as smart glasses, we present our system iBlink to prevent the facial paralysis patients from such eye damage. There are several challenges to the main idea of our system is to monitor the normal side of the face and stimulate the paralyzed side so that the eye movement of the both sides can become symmetric. There are some challenges to overcome in the design of our system. First, our system has to accommodate to the individual diversity. From the EMG traverse, we can see that different patients require different configurations of stimulation, and their blink frequency also varies, and the different eye tube degrees can increase the difficulties for eye blink detection. Second, because the illumination conditions influence the detection accuracy and not, and the illumination conditions is always changing with time and the mobility of the user. Therefore, our system also has to accommodate the environment changing. Third, our system has to be power efficient, which is a common challenge for most of mobile devices. Here is the design structures of our system. It includes the hardware module and the software module. In the hardware module, the eye is installed in front of the eye and monitors the eye movement in real time. The Raspberry Pi platform can process the images captured by the eye camera The electrodes are pressed on the fashion skin, and the Wi-Fi and Bluetooth interface in the Raspberry Pi platform can support the communications between our system and smartphones. Our software layer consists of 4 layers. The input layers can capture the image data and ambient light data from camera, and the pen control data from pen switch. The processing layer deals with the data sent from the input layer, and the execution layer handles the stimulation control and the sampling control. The communication layer can collect the pathology data of the patients and send them to the doctor if needed. Next, I will introduce our facial image processing. In our facial image processing, we use 2 fixed windows to cut single-eye images. We train our CAN model with the single left eye image and the flip of the right eye. We train 2 kinds of CAN model for daytime and nighttime, considering different illumination conditions. Here is the design and training process of our CAN network. It includes 3 convolutional layers and 1 fully connected layer. We train our CAN model with more than 30,000 images from 12 different people. We have published our image library on the website, or you can scan the QR code to get the resources of our library. The library can support for the further study on the facial paralysis. With the CAN features, we can implement a classifier to label 1 as eye open and 0 as eye closed. And since the normal blink action takes about 200 milliseconds to 400 milliseconds, and the sampling rate of our camera is about 20 to 30 frames per second, there will be multiple frames in a single blink action. Because false detections may happen, we introduce a purring cursor to identify a blink action. A blink action is identified only if zeros are the majority in empty sampling result. NP is set to 3 in our system. However, in the new versions of our system, we want to use the Raspberry Pi Zero because it's small, it can limit the size of our system. But the Raspberry Pi Zero platform cannot support the CAN framework. Therefore, we introduce a new algorithm for blink detections. In the new algorithm, we first use the local binary pattern to obtain illumination invariant and rotation invariant features. Then we divide the LPP map into several blocks to enhance the details and calculate the histogram to limit the dimensions of the features. Then we use PCA to compress the dimension of our features. Finally, we use SVM classifier for labeling the iBlink status. Here is the introduction of our stimulation circuit. This figure is the working procedures of our stimulation circuit. In the red amplifying group, the eye camera monitors the feedback of the patients, and the Raspberry Pi can send out PWM waves to the amplifying circuit. The amplifying circuit taking the waves and amplifying to the output voltage. In the green control loop, the level control circuit takes in the GPIO control signals from the Raspberry Pi and the pen switch input to adjust the output voltage level to satisfy the different requirements of different patients. The amplifying circuit consists of 3 bipolar junction transistors, 1 transformer, and several resistance to amplify 3.3 volt PWM raised to about 200 volt output voltage. Although the output voltage is very high, but itself, single stimulation lasts only less than 3 milliseconds. The level control circuit contains a switch chip CD4066B and a potentiometer. The switch chip can take in the GPIO control signal sent from the Raspberry Pi and adjust the output voltage level by switching the resistance to different values. And the potentiometers allow the patients to adjust the output voltage manually. As mentioned before, different people have different thresholds for stimulation, and the surrounding environment is always changing. Therefore, to avoid pain or discomfort, we set up 4 modes for our system. In the setup mode, the stimulation voltage starts from 0 level, and it will increase level by level until a blink is detected. And the ambient light intensities can determine the selections of daytime and nighttime mode. Once pain or discomfort happens, the patient can close their healthy side eyes for a certain time TP. This will trigger the pain control mode. In the pain control mode, the stimulation level will decrease until a new critical point is found. Here is our pain control mechanism. The main idea of our mechanism is to keep decreasing the output voltage level until it finds a new appropriate one. To exactly capture the eye movement, the sampling rate of our camera should neither be too high to consume too much power, nor too low to use useful information. We set the upper bound of our sampling interval 15 milliseconds to ensure at least 3 blinks can be captured in a single blink process. And the lower bound 33 milliseconds according to the highest frequency of our system. To obtain an appropriate sampling frequency, we calculate 2 neighboring blink intervals. If the decreasement of the blink interval is larger than the threshold, then we'll increase our camera sampling frequency also, because the patients have the tendency to increase their blink frequency. Here is the algorithm of our sampling control algorithm. We also developed apps to achieve the communication between our system iBlink and the smartphone. Here is some screenshot of our apps. From the left to right is the data request page, data analysis page, and the zoom view of this page. In total, our system consists of a stimulation circuit, eye camera, electrodes, Raspberry Pi platform, and a power unit. This is the working prototype of our system. We also conduct some experiments to evaluate the performance of our system. We first test the detection accuracy after different illumination. Based on this result, we set the daytime and nighttime switching point 15 next. And we can see from the figure, our system can achieve a very high accuracies in iBlink detection, except for extreme case, which is rarely happen in daily life. This figure shows the stimulation voltage for each stimulation level. The range of the voltage is not equal because we want the stimulation level at a high value can increase slowly in case of pain or discomfort, because a sudden increase will trigger pain or discomfort. This figure shows different stimulation level on the different working mode. The first is setup mode. We can see that the stimulation level starts from 0 and increase level by level until a blink is detected. Then in the pain control mode, maybe a pain or discomfort happened. The stimulation levels start decreasing until a new critical point is finding. We also conduct a power consumption. This result can show that 7.4 power pack can support our system usage but at least 10 hours. The final is some images about our experiment conducted on patient volunteers in our hospital. Here is the GIF. That's all. Thank you for your listening.